Alright, for the Equilibrant Lab, you're going to have the force table, you're going to have the force springs, and you need a piece of paper on it. Find a place to anchor the springs, and then make sure there's a certain amount of tension on the gauges. You can go above 10 if you like, but it doesn't really matter. Center your paper roughly in the middle, and put a dot right inside the circle. At that point, you're going to hold down the force springs, put a line on each side of them, and then record what they say. This one says 567.8. This one says 7.2. And this one says 6.5. Okay, once you're done, you can remove this and remove this entirely. Oops. There should be a line on each side of your scale, and what you're going to have to do is find the midway point between those lines. Each one is approximately 15 centimeters apart, so if you go in 7.5, you should be able to find the midway point. Midway point. Oop. 7.5. And midway point. Okay, draw a line between the center point and the midway point all the way down. This is a guideline. This is the direction of each of your three vectors. I'm going to call them T1, FT1, FT2, and FT3. If you want to call them F1, F2, and F3, you can. Since this is 6.5 newtons, 7.2 newtons, and 7.8 newtons, I'm going to use a 1 centimeter to 1 newton scale. If you had a smaller force, you could use a 2 centimeter to newton scale. If you had a larger force, you could use a 2 newton to 1 centimeter scale. So if I go out exactly 6.5 centimeters, I should end up out here, 6.5. Be exact as you can about this length. Okay. 7.2 centimeters goes out and ends out exactly here. And then 7.8 centimeters comes out to right here. Do need to extend this line a little bit. Okay. Now you're going to declare a set of axes. It really doesn't matter which ones you use, but I'm going to line up with pretty much the angle of the paper. Actually, I'm going to put a bit of angle just to emphasize something. Make sure your axis goes to the center point. This is my y-axis. And then if I put the center hole and the 90 on the line, I can get a perpendicular line to that one. I'm going to call this the x-axis. Okay, so y and x. At this point I have three vectors, f1, f2, and f3, and they're going off at angles away from the axes. So the point is, if I take any two vectors and combine them together, I should get the opposite of the third one. That's the resultant, or the equilibrant. So I need to take this line and translate it from here up to here. Okay, so in order to slide this up here, I need to find out what this angle is. And I'm going to measure it by putting the hole in the center, line this up with the line, and this is coming across at the 12 centimeter line. 10, 12, count up, don't count backwards. This is a 12-degree angle. So if I were to get a second x-axis through this point, I line up the hole with the axis, I line up the 90 with the axis, and line up the base of the thing. This line right here is parallel to my x-axis. I'm going to call it x prime, just for lack of a better term. So if I were to come up 12 degrees from the x prime axis, I should get a parallel line to this one. So I'm going to put this here, find the center in there, line up the line, and then go out exactly 12 degrees, which is right here. Okay. So this line is where I'm going to put that line. Oh, you can tell right now that I made a mistake somewhere, and that's not parallel. So let me erase that and get rid of it. Okay. Let me double check my angle. I misread this. 10 is here, 15 is here, 20 is here. This is a 17-degree angle. Please make sure you read your protractor carefully. So I need to go up 17 degrees from where that was. Again, I find the line on the base, put the hole at the center, and I want to go up 17 degrees right here. Okay. This line is now, should be, parallel that one. And honestly, if it looks parallel, it probably is. Alright, so to transpose or transfer this vector over here, I need to go out 6.5 newtons. So along this line, I go 6.5 centimeters. And there's where I end up being. So that vector right there, right here, with the arrowhead, is FT1. Okay, is FT2. So at that point, here's another 12-degree angle. I've got this. If I complete this one and translate it over here, it would have a parallelogram. So if I were to go from here, from the origin to the end of that point, this vector here is FT1 plus FT2. Technically it's FT2 plus FT1, but you know what I mean. And when I measure it, I get exactly 7.9 newtons. 7.9 newtons. So I'm going to circle this here, I'm going to circle this here, and look, it is in the opposite direction, roughly, and it's of opposite magnitude. So if I were to take F3, put it this direction, it would take me back to the origin. So these three forces cancel out. You can tell because any two of them added together makes a vector that will cancel out the third one. This is the first proof.